Okay, so in the last video ended, we had just finished the one about incandescent and fluorescent lights. And we were moving to the number 47 about microwaves, but maybe just for a second before we leave the fluorescent and incandescent lights. So the fluorescent is still pretty inefficient. It only has an efficiency of 8.3 repeating percent, but it's twice as efficient as the incandescent. Where does all the rest of the heat go? It goes in, or where does all the rest of the energy goes? It goes to heat. And you've probably noticed this if you've ever tried to change a light bulb. If it's been on for a while, a regular light bulb, and it's been on for a while and then it goes out, it pops, and you go to change it, it's really, really, really hot. That they would be incandescent. It's also why most light bulbs in our school, I think probably I'm safe saying all of them, are fluorescent. Twice as efficient, even though still horrendously inefficient. They still give off a ton of heat, and that's why a lot of teachers in their classroom, when it gets warm in the spring, would keep their lights off so they're not giving off heat. I don't do that because then people fall asleep and I can't see. There's a third type of light bulb. They're called compact fluorescent. They're the ones that are scrolly. You know, you probably have them. And they're supposed to be a lot more energy efficient than even the fluorescent. The problem is they also have mercury inside of them, so we don't have a great way of disposing them. When they first came out, governments were giving them to people, wanting people to switch over. But it didn't take very long before they realized that these aren't great for everyone. One, because we don't have a way of recycling them well. And we don't want all that mercury that's inside of them to end up in the landfill. But the other problem is because they're more efficient, they don't give off as much heat. And there are a lot of people in our town, city, country, province, country, world who use light bulbs as a heat source, right? So instead of paying for heat, they turn the lights on and then they can see and they heat up their homes like with those light bulbs. Anyway, I just thought since we were here, I should probably mention that. All right, back to number 47, which was the microwave. It says it transforms 345 joules of radiant energy into 301 joules of thermal energy. So what you get out is 301 joules. What you put in is the 345. That's what's coming from the wall socket. And the 301 is what's being used to heat your food. And so the efficiency then of a microwave is really not all that bad. It's 87.246%. Wouldn't have been that high when they first came out, but they are now. All right, number 48. I'm just looking for another page to finish these. 48, maybe, that was 48. 49 might seem a little bit weird, but they try to walk you through it. So they say a ball of mass 125 grams, which of course you have to change to kilograms, so 1.125, is thrown with a force of 85 newtons. So F is 85 newtons, and you're throwing it, applying that force over a distance of 0.78 of a meter, 78 centimeters. The ball's velocity just before it's caught is 9.84 meters per second. So the V final, 9.84 meters per second. So remember our equation, work done is equal to the change in energy. So in my perfect ideal world, all of the work done will be converted into the change in energy. So my F delta D will be my energy in. And my change in energy, and in this case it's kinetic because it's changing speed, 1/2 mvf squared minus 1/2 mvi squared, where vi is 0. This will be my energy out. Okay, so my energy in then is 85 newtons times 0.78 meters. And that's what the first question says, how much work, first part A says how much work is done, 66.3 joules. Part B wants to know what kinetic energy does it have just before you've caught it. And so that's your kinetic, 1/2, which is your energy out, 1/2 mv squared. So that's your E out. So your E out, or your kinetic energy, 1/2, what was it, 0.125 kilograms. And your speed was 9.84 meters per second squared. So your kinetic energy, your E out, is 6.0516 joules. Okay, and then part C says, well, it's kind of weird. So first let's find the efficiency, because the efficiency will be the out over in times 100. So it'll be 6.0516 joules over 66.3 joules times 100. So your efficiency ends up being 9.1276%. But if you look at question C, that's not what it asks. It asks how much is lost. Well, if this is how efficient it is, this is the percentage that's saved. So the percentage that's lost will just be 100 minus that. So it'll be 90.8724% will be the amount that's lost. Okay? And the last question, number 50. Rubbing your hands together requires 450 joules of energy and results in an increase in your palm and thermal energy of your palms of 153. Calculate the efficiency. Need another piece of paper. I'm going back to this one. So number 50 is really straightforward. It gives you the in, it gives you the out. You just stick them in the equation and multiply by 100. So on the top will be 153 joules. On the bottom will be your 450 joules times 100. And you should get an efficiency of 34% done. Okay?